morning, people. I hope you're doing well, my delovelies. So, let's get to the bottom of something that may contain science. Specifically, the bottom of the ocean. There's tons of science down there. But, as researchers in the journal Scientific Advances recently demonstrated, there's so much ocean at the bottom of the Pacific. There's even ocean under the ocean. Okay, Sam. What the absolute heck does that actually mean? Well, it has to do with the Earth's crust and how its tectonic plates interact. So, first, let's review that. Here is the Earth. That's as a sweet Earth, you might say. Well, this particular map of Earth shows our tectonic plates, and the colors at the edges of the plates indicate the way those boundaries move and interact with one another. Broadly speaking, there are 3 types of boundaries between these plates based on the direction each plate is moving. The San Andreas Fault, near me, is a transform boundary. The sort of mustard yellow line. Those faults slide against one another laterally, creating the quaking vibrations that range from SoCal locals won't get out of bed for this to the big one. But there's other ways these plates can interact. If you look at the red lines between plates, like the ones down the Atlantic Ocean, those are divergent boundaries. That means they're pulling away from one another. As the gap between the plates widens, you get a rift, then a rift valley. You can see one of these plate boundaries goes right through actual Iceland. It looks like this in real life. Eventually, once the rift is wide enough, molten magma below the Earth's crust rises up to fill the gap, so at a lot of these divergent boundaries, you'll see mid-ocean ridges. But if a plate is pulling away on one edge, it's often pushing on another edge. That's a convergent boundary. And these zones often have a bunch of earthquakes, volcanic activity, and general happy fun times as the plates push into one another until one gives way and drops under the other. That process is called subduction, and it's what brings us to the sea under the sea we're talking about today. The fault at fault, so to speak, is the Hikurangi subduction zone, where the Australian plate meets the Pacific plate near New Zealand. Like most matchups between continental plates and ocean plates at subduction zones, the Australian plate is winning, slowly pushing itself over the Pacific plate. So far, pretty normal plate boundary, right? But what about the Hikurangi Plateau on this map? It was created by volcanic activity in the early Cretaceous, entirely unrelated to the late Cretaceous Deccan traps volcanism from our previous episode. And this is all part of the volcanic happy fun times that come with the convergent plate boundary, right? Well, those times were particularly fun, as this event was one of the largest known volcanic eruptions in the history of Earth, going on for literal millions of years and creating this plateau. Our researchers performed seismic scans at the plateau at the fault line, right where that little red rectangle is. They also drilled for core samples to confirm the composition of the rock and found it was wet. And it might not seem weird to us that rock under the ocean is wet because, it's under the ocean. But we're talking under, like under. The working theory is that as local seas eroded the Hikurangi volcanoes, the ones that erupted for literal millions of years, into porous rock, that rock then took on water like an aquifer, and as the Australian plate continued to win out and push over the Pacific plate, the rock took that water with it, trapping it under the ocean's crust. In this case, the volcanic crust of the subducting Hikurangi Plateau is almost half water by volume. So yeah, okay, this isn't a sea under the sea in a way that, like, we could go for a swim. But it means that unlike your average subducting oceanic plate, the upper crust here is hydrated. Typically, after a few million years, subducted crust dries out, or dewaters is the technical term. So the fact that this much older, like Cretaceous era crust hasn't dried out yet may be attributable to the specific circumstances right at this particular boundary. Indeed, our researchers credit this captured water for New Zealand's so-called slow slip earthquakes. So rather than one big mega shake like the ones that occur at my local strike slip fault, the Hikurangi subduction zone has quakes with the same energy released as a mega shake, but instead spread out over weeks, months, or even years instead of minutes. Now, that's a good thing. It can serve to dissipate the stress between plates harmlessly, and apparently, the water from the subduction zone may actually act as a lubricant to enable this type of slow slip. Lab experiments and simulations have led seismologists to predict that fluid disposition might enable slow slip events, but this is the first physical evidence to support that hypothesis. Now, we'll have to drill deeper down to really confirm how deep this water goes and how it affects the pressure situation at the fault line. If we know just how much water there is, where it is, and the pressures it's under, we'll have a much clearer picture of how that fluid reservoir, the sea under the sea, affects the fault and how it contributes to slow slip events. Well, does this research suggest that New Zealand's safe from seismic phenomena is only going to experience these harmless little slow slips? No. I'm sorry. Unfortunately, no. At the end of the day, there are still two entire tectonic plates shoving into one another, and there's plenty of plate boundary that's not nearly as hydrated as a Hikurangi subduction zone. And even with all that hydration, the subduction zone's still the largest source of earthquake and tsunami hazard in the area. But the more we understand the composition of these plate boundaries and how they interact, the more effectively we'll be able to predict seismic phenomena, which is important to, well, just about everyone on the planet Earth, even those who aren't directly near a plate boundary themselves. Our sea under the sea in New Zealand may not be like a proper underwater body, not like the subglacial lakes of the Antarctic. But if it's even slightly easing the transition of one tectonic plate under another, it seems pretty good to me.